Hello everyone and welcome back. From the previous session itself, we have been learning about the instruction types which provide the rotating functionality of the accumulator's content. Continuing that streak, today we are going to learn about two more instruction types, RRC and RAR, which will also help us rotate the accumulator's content but to the right. So without any further ado, let's get to learning. Coming to the topics that we are going to cover in this session, today, at first we will learn about the instruction type RRC and thereafter we will learn about the instruction type RAR. So let's begin with the first instruction type of the day, RRC. Coming to the instruction type RRC, it stands for rotate right the content of the accumulator and in that process send a copy of that least significant bit to the carry flag. In order to understand how this instruction will work, let's understand the organization at first. If you notice, this organization is just the opposite to the previous instruction type that we learned in the previous session, which was RLC. RLC stands for rotate left accumulator's content, and in that process, we are also supposed to send a copy of the most significant bit to the carry flag. But in this case, notice the organization. The direction of the loop is from the least significant bit towards the most significant bit. So clearly, with the execution of the instruction RRC, the contents of the accumulator will be shifted towards the right. Therefore, the least significant bit within the accumulator will come out, and before it is sent to the most significant end and becomes the most significant bit of the accumulator's content, a copy of that least significant bit will also be sent to the carry flag. And this is just the opposite of the instruction RLC. If you remember, in the previous session when we learnt about the instruction type RLC, the most significant bit's copy was being sent to the carry flag. And that bit eventually became the least significant bit. But in case of RRC, we are supposed to rotate right the accumulator's content and in that process send a copy of that least significant bit to the carry flag. Coming to the instruction type RRC, this instruction falls under the 1 byte long instructions category and it can be used for checking the value of the least significant bit. That is, since we are sending a copy of the least significant bit to the carry flag, we can judge whether the least significant bit is 0 or 1. This instruction can also be used in order to perform division by 2. If you remember, we also have learned this in our previous chapters. When we perform shift by 1 bit, it means division by 2. So 2 shifts towards the right will mean division by 2 squared or 4. Similarly, 3 consecutive shifts will mean division by 2 cubed or 8. Therefore, in order to perform the division by 2 raised to the power n, we will have to shift the content of the accumulator n times. Let me now show you how it will work using an illustration. Say within the accumulator, initially we have got the value 48. Notice the least significant digit, it is 8. The 4-bit binary equivalent of 8 is 1 followed by 000. What about 4? The equivalent 4-bit binary of 4 is 0100, right? Now if we execute the instruction RRC, as I told you earlier, the least significant bit will come out of the accumulator and a copy of this bit will also be sent to the carry flag. Now as you can notice, since the least significant bit fell off the accumulator, therefore it has created an empty space in here. So all the remaining bits can shift towards the right by 1 bit. Now you can also notice this, in the process of shifting, we created an empty space at the most significant bit's place. The least significant bit, which was previously 0, will now be placed in that most significant bit's place. Now notice the content of the accumulator, 0010 followed by 0100. Now in terms of hexadecimal, 0010 is 2 and 0100 is 4. So after the execution of the instruction RRC, within the accumulator we now have the value 24. So before the execution of the instruction RRC, within the accumulator we had the value 48, which after the execution of the instruction RRC has become 24. If you notice, 24 is actually the half of 48. So here, the division by 2 principle holds. Basically, shifting the contents of the accumulator towards the right, we actually have performed division by 2. Remember, we just executed the instruction RRC once. If we want to further divide the content of the accumulator, all we have to do is keep on shifting the bits towards the right. Now the question is, will this be the result all the time? Well, no. And let me show you that using an illustration. Say for this time, within the accumulator, we have got the value 49. Now the 4-bit binary equivalent of hexadecimal 9 is 1001. What about 4? We already know this, it is 0100. Notice, if we execute RRC, the least significant one will come out. And in the process, we are also supposed to send a copy of this to the carry flag. Since the process of shifting has created an empty space in the least significant bit, all the bits now can be shifted towards the right, one bit at a time. In this process, the most significant bit space is again empty. So the least significant bit, which was previously 1, will now become the most significant bit. Now notice the content of the accumulator. 1010 followed by 0100. Now 1010 is 10 or A in case of hexadecimal. What about 0100? We are quite familiar with this bit sequence. It is 4. So before the execution of RRC within the accumulator, we had the value 49, which after the execution is A4. Notice the content of the accumulator before the execution of RRC and after the execution of RRC. Is A4 half of 49? Well, no. Rather, A4 happens to be much bigger value than 49. So did we do something wrong in here? Well, not really. When we are shifting the bits towards the right, do remember we are also replacing the most significant bit. So if the most significant bit, which was previously 0, now becomes 1, will carry more value than the previous number. So clearly, if in the least significant bit we have got 1, execution of the instruction type RRC, since it rotates the content of the accumulator and makes the least significant bit the most significant bit, is not going to result in the half of the value. In order to have the half of the previous value after the execution of RRC, we have to make sure that the least significant bit was 0 before the execution. So that was all about the instruction type RRC. Do remember, this instruction rotates right the contents of the accumulator and sends a copy of the least significant bit to the carry flag. Using this instruction, we can always check the least significant bit by judging the contents of the carry flag after the execution of this instruction. Another thing to note down, the instruction RRC falls under the category of 1 byte long instructions, and it just performs the opposite of the instruction type RLC, which helps us rotate the contents of the accumulator towards the left and in the process sends a copy to the carry flag. Let's now learn about the next instruction type, RAR. Coming to the instruction type RAR, it stands for rotate accumulator right involving the carry flag. Does it remind you of any other instruction type? Well, in the previous session, we studied about the instruction type RAL. In that instruction, we were rotating the contents of the accumulator towards the left, involving the carry flag. But in this case, we are rotating the contents of the accumulator towards the right. So for this instruction, the organization is going to look something like this. Notice, It is just the opposite of the instruction type RAL which we have learnt in the previous session. Now if you observe carefully, here the least significant bit of the accumulator after the execution of the instruction RAR will be shifted in the carry flag's content. And whatever the carry flag is going to hold prior to the execution of the instruction type RAR will become the most significant bit after the execution. Well, worry not, I'll illustrate the entire process using an example. For now, just remember RAR stands for rotate accumulator's content right, but this time we are going to involve the carry flag. Now coming to the instruction type RAR, it also falls under the 1 byte long instructions category. And using this instruction, we can either check the value of the least significant bit. The reason is the same as the instruction type RRC. Since the least significant bit is going to be shifted to the carry flag, therefore, after the execution of the instruction, we can judge the content of the carry flag to find out the value of the least significant bit. Furthermore, we can also perform division by 2 using the instruction type RAR. But this time, we have to make sure that the carry flag's content prior to the execution of the instruction type RAR should be 0. And the reason for that is, the carry flag's content eventually will become the most significant bit within the content of the accumulator. And we already know, since the most significant bit carries the most of the value of the entire bit sequence, therefore, if we alter the most significant bit to be 1 after the execution of the instruction RAR, that will increase the value, which cannot be the result of a division. Because division generally decreases the value, right? So anyway, if we choose the carry flag's content carefully, we can also perform division by 2 using the instruction type RAR. Now you might be wondering, then what is the usage of RAR? Well, it is mainly used to introduce a new bit as the most significant bit. If you remember in the previous session when we were learning about the instruction type RAL, using the carry flag, we could introduce a new bit as the least significant bit. This time, since the carry flag's content will eventually become the most significant bit within the content of the accumulator, therefore, if we choose the carry flag's content as per our desire, we can introduce a new bit as the most significant bit. Let me illustrate how we can do that. Say within the accumulator, we have got the value 2, 1. Now the 4-bit binary of 1 is 0001. What about 2? You all know it, it is 0010. Now look at the most significant bit currently, it is 0. Say we would like to change this. And for that, we are choosing our carry flag to be 1. Now notice, if we execute RAR, since we are supposed to rotate the accumulator's content towards the right, so the least significant bit, which is 1, will come out. And this will be placed inside the carry, making the previous content of the carry, which was also 1, come out of the carry flag. This process created an empty space in the least significant bit's place. So all the remaining bits can be shifted towards the right one at a time. In this process, the most significant bit's place is now empty. So the content of the carry flag, which was 1, can now become the most significant bit. I hope you noticed this. Previously, the most significant bit was 0. Since we chose the carry flag to be 1 prior to the execution of the instruction RAR, now as you can see, that content is the most significant bit. So clearly, we introduced a new bit as the most significant bit. Now look at the content of the accumulator. It is 1001 followed by 4 zeros. So the accumulator now has the value 90. 9's 4-bit binary is 1001 and 0 in binary is 4 zeros. Also look at the content of the carry flag. Since the least significant bit of 2, 1, that is 0010 followed by 0001, was 1, so the carry flag's content remained unchanged. So this was the content of the accumulator and the status of the carry flag prior to the execution of RAR. And after the execution of RAR within the accumulator, we now have 90, and the content of the carry flag is also the same, and the reason for that is the least significant bit was also 1. However, since we chose the carry flag to be 1, we introduced a new bit as the most significant bit. So this is how, using the instruction type RAR, we can rotate the accumulator's content right involving the carry flag. Do remember, in this process, we can always check the content of the carry flag, which is going to hold the least significant bit. So we can also say, after the execution of the instruction RAR, we can judge what is the value of the least significant bit. Also, if we reset the carry flag's content prior to the execution of the instruction type RAR, execution of the instruction RAR will convert the value of the accumulator into its half. Apart from these two, we can also use the instruction RAR to introduce a new bit as the most significant bit. Also remember, the instruction type RAR, just like the previous one, falls under the 1 byte long instructions category. So with these two instruction types, we now have covered all the instructions of the logical group of instructions. What I'm trying to say is, we learnt about all the different instruction types of logical group of instructions, and in that process, we actually covered 43 opcodes. So in this session, we covered the topics, the instruction type RRC and the instruction type RAR. Remember, both of these rotate the content of the accumulator towards the right, where RRC sends just a copy of the least significant bit to the carry flag. On the other hand, the instruction type RAR, it involves the carry flag's content in the rotation process. Both of these instructions fall under the 1 byte long instructions category. Alright people, that will be all for this session. In the next session, we are going to learn about the summary of logical instructions. In other words, we will quickly revise all the different 15 types of logical instructions, and during the revision, we will ensure that we actually have covered 43 different opcodes. So I hope to see you in the next one. Thank you all for watching.